NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve a polynomial problem exactly following the structure shown. Factor, find the roots, and build a sign table to understand where the expression is positive, 0, or negative. We start with the expression capital A equals x to the fourth minus 13x squared plus 36. Now we factor it into two quadratics. Left parenthesis x squared minus 4 right parenthesis times left parenthesis x squared minus 9 right parenthesis equals 0. Next we apply the difference of squares to each quadratic. That gives left parenthesis x minus 2 right parenthesis, left parenthesis x plus 2 right parenthesis, left parenthesis x minus 3 right parenthesis, left parenthesis x plus 3 right parenthesis equals 0. Now set each factor equal to 0 and solve. X minus 2 equals 0, so x equals 2. X plus 2 equals 0, so x equals negative 2. X minus 3 equals 0, so x equals 3. And x plus 3 equals 0, so x equals negative 3. To complete the structure, we construct a sign table. The columns will be the x markers negative infinity, negative 3, negative 2, 2, 3, and positive infinity. The rows will be x minus 2, x plus 2, x minus 3, x plus 3, and finally capital A, the product of all four factors. We will fill the zeros at the roots and determine signs on the intervals between them from the factorization. And the sign table, we see the zeros occur exactly at x equals negative 3, negative 2, 2, and 3. On the intervals, the product is positive before negative 3, positive between negative 2 and 2, and positive after 3, while it is negative on the intervals between negative 3 and negative 2, and also between 2 and 3. In this lesson, we will determine the domain and the sign of the rational expression A equals negative 5 divided by the product of x plus 2 and x minus 3. Our task is twofold. 1. Find all x values for which the expression is undefined. 2. Use a sign chart to decide where A is positive and where A is negative. Step 1. Set each factor in the denominator equal to 0. X plus 2 equals 0 gives x equals negative 2. X minus 3 equals 0 gives x equals 3. These two values make the expression undefined and will split the number line into three intervals. To determine the sign, we multiply the signs of three factors, the constant negative 5, the factor x plus 2, and the factor x minus 3. We will fill a sign chart across the three intervals. We can now state the domain and the sign behavior. The domain is all real numbers except x equals negative 2 and x equals 3. The expression A is negative on the intervals from negative infinity to negative 2 and from 3 to infinity. It is positive on the interval from negative 2 to 3. Example, we will analyze the sign and domain of the rational expression D equals open parenthesis x minus 1 close parenthesis over open parenthesis 5 minus 2x close parenthesis. Write the expression clearly. Our goal is to find where it is positive, negative, or 0, and to identify excluded x values. Step 1. Find the critical x values. Set the numerator x minus 1 equal to 0, giving x equals 1. Set the denominator 5 minus 2x equal to 0, which gives x equals 5 halves. This value makes the denominator 0 and is excluded from the domain. Now let's construct a number line to organize the sign analysis. We'll place two markers at x equals 1 and at x equals 5 halves. We will label both points and mark 5 halves with a vertical bar to show it is excluded. First, the numerator. The expression x minus 1 is negative to the left of 1 equals 0 at 1 and positive to the right of 1. Next, the denominator. The expression 5 minus 2x is positive when x is less than 5 halves, equals 0 at 5 halves, and negative when x is greater than 5 halves. Finally, combine the signs. A quotient is positive when numerator and denominator have the same sign, negative when they have opposite signs, and 0 only when the numerator is 0 while the denominator is not. At x equals 1, the numerator is 0 and the denominator is not, so D equals 0. At x equals 5 halves, the denominator is 0, so the function is undefined. We show this with a bold magenta bar at 5 halves. In this lesson, we will determine the sign of a rational expression by building a clean sign chart. Our expression is capital A equals the quantity x plus 3 times x minus 4, all over negative 3 times the quantity x plus 1. We will follow 3 steps. Rewrite, find critical numbers, and then fill a sign table to combine signs interval by interval. Step 1. Rewrite. We can also view the denominator as negative 3x minus 3. This does not change the value, but it lets us list linear factors clearly. Step 2. Critical numbers. Set each linear factor equal to 0. From x plus 3 equals 0, we get x equals negative 3. From x minus 4 equals 0, we get x equals 4. From negative 3, x minus 3 equals 0, we get x equals negative 1. Because that factor is in the denominator, x equals negative 1 is excluded from the domain. Step 3. The sign chart. We mark the critical x values in increasing order: negative infinity, negative 3, negative 1, 4, and positive infinity. Then we make one row for each linear factor and a final row for capital A. We will fill signs left to right. First row, x plus 3. To the left of negative 3, it is negative. At x equals negative 3, it is 0. And to the right, it is positive everywhere. Second row, x minus 4. It is negative until x equals 4, 0 at x equals 4, and positive afterwards. Third row, negative 3x minus 3, which is the denominator factor. It is positive when x is less than negative 1, 0 at x equals negative 1, and negative after that. Last row, combine the signs. A is the numerator sign divided by the denominator sign. On the interval negative infinity to negative 3, the result is positive. At x equals negative 3, A equals 0 because the numerator is 0. Between negative 3 and negative 1, the result is negative. At x equals negative 1, the expression is undefined. So we mark a barrier line. From negative 1 to 4, it is positive. At x equals 4, it is 0. And after 4, it is negative. Summary. The domain is all real numbers except x equals negative 1. The expression A is greater than 0 on the intervals open negative infinity to negative 3 and open negative 1 to 4. The expression A is less than 0 on the intervals open negative 3 to negative 1 and 4 to infinity. A equals 0 at x equals negative 3 and x equals 4. Example. We will determine the sign of a rational expression using a sign chart. Our expression is A of x equals open parenthesis x minus 2 close parenthesis times open parenthesis x minus 3 close parenthesis divided by x times open parenthesis 1 minus x close parenthesis. We will 1. Find critical numbers from each factor. 2. Mark denominator roots as not allowed. 3. Fill a sign table and then read off where the function is positive, negative, or 0. Let us solve each factor equal to 0. X minus 2 equals 0 gives x equals 2. X minus 3 equals 0 gives x equals 3. X equals 0 comes from the factor x in the denominator, and 1 minus x equals 0 gives x equals 1, also in the denominator. The fraction is undefined at x equals 0 and x equals 1. Now, we will build a sign chart. Columns will be the intervals split by the critical numbers, together with single columns for the special points 0, 1, 2, and 3. Row 1. X minus 2 is negative before 2, 0 at 2, and positive after 2. Row 2. X minus 3 is negative before 3, 0 at 3, and positive after 3. Row 3. The factor x is negative before 0, 0 at 0, and positive after 0. Row 4. 1 minus x is positive before 1, 0 at 1, and negative after 1. Now multiply the signs of the numerator and divide by the signs of the denominator to get the sign of A of x. Remember, at x equals 0 and x equals 1, the function is undefined. Evaluating interval by interval gives negative on minus infinity to 0, positive on 0 to 1, negative on 1 to 2, 0 at 2, positive on 2 to 3, 0 at 3, and negative after 3. Summary. Negative on minus infinity to 0, positive on 0 to 1, negative on 1 to 2, 0 at 2, positive on 2 to 3, 0 at 3, and negative after 3. Summary. The domain is all real numbers except 0 and 1. A of x equals 0 at x equals 2 and x equals 3. It is positive on the open intervals 0 to 1 and 2 to 3. It is negative on minus infinity to 0, 1 to 2, and 3 to infinity. This is the standard sign chart method. List factor zeros, mark denominator exclusions, fill factor signs across the intervals, and then multiply signs to get the sign of the function. In this lesson, we will determine the sign of a rational expression using the classic factor sign chart. Our example is capital A of x equals negative x times x minus 1 times x minus 2, all over x minus 3 times x minus 4. We'll follow 3 steps. Find zeros and restrictions, build the sign chart for each factor, and then combine the signs to get the sign of A on each interval. Step 1. Find all zeros of the numerator and the restrictions from the denominator. Setting each factor equal to 0 gives us the following list. Negative x equals 0 implies x equals 0. X minus 1 equals 0 implies x equals 1. X minus 2 equals 0 implies x equals 2. For the denominator, x minus 3 equals 0 implies x equals 3, and x equals 4. These are restrictions and cannot be included in the domain. Step 2. Build the sign chart. We mark off the critical numbers in order: 0, 1, 2, 3, and 4. We will include the open intervals between them as separate columns. Then, we fill a row for each factor showing plus, minus, or 0 on each interval, with a special highlight for the restrictions at 3 and 4. Step 3. Combine the signs of the numerator and the denominator. We multiply the signs of the numerator factors negative x, x minus 1, and x minus 2, and then divide by the sign of the denominator factors x minus 3 and x minus 4. We also place zeros at x equals. Step 3. Combine the signs of the numerator and the denominator. We multiply the signs of the numerator factors negative x, x minus 1, and x minus 2, and then divide by the sign of the denominator factors x minus 3 and x minus 4. We also place zeros at x equals 0, 1, and 2, and mark x equals 3 and 4 as undefined. Watch the bottom row fill in. From the sign row, we read our complete answer. The domain excludes x equals 3 and x equals 4. A of x is positive on the intervals negative infinity to 0, 1 to 2. Wait, correct that. Positive on negative infinity to 0, 1 to 2 produces positive? Check. It is positive on 1 to 2. Yes, negative on 0 to 1, and on 2 to 3, positive again on 3 to 4, and negative after 4 to infinity. And it equals 0 exactly at x equals 0, 1, and 2. That is the complete sign analysis for the rational function using a factor table. When the factors are listed in order and the critical numbers are marked, the signs practically compute themselves. Practice this approach with different numerators and denominators to build speed and accuracy. In this example, we will determine the sign of the expression A of x equals the absolute value of x times negative 2x plus 4, all over x squared. We will follow 3 steps. First, locate critical points from the zeros of the numerator and the denominator. Second, note any excluded points where the denominator is 0. Third, build a sign chart to decide the sign of A on each interval. Step 1. Find zeros. The numerator is the absolute value of x times negative 2x plus 4. Absolute value of x equals 0 implies x equals 0. Negative 2x plus 4 equals 0 implies 2x equals 4. So x equals 2. The denominator is x squared. So x squared equals 0 implies x equals 0. Step 2. Mark excluded points. Because the denominator is x squared, x equals 0 is not allowed in the domain of A. We exclude x equals 0, and we keep x equals 2 as the only 0 of the whole fraction. Step 3. Build the sign chart using the critical points 0 and 2. We analyze the sign of each factor on the intervals negative infinity to 0, 0 to 2, and 2 to infinity, and then combine the signs. Absolute value of x is positive everywhere except at 0, where it is 0. Negative 2x plus 4 is positive when x is less than 2, is 0 at 2, and negative when x is greater than 2. The denominator x squared is positive for every x not equal to 0, and 0 at x equals 0. Therefore, the sign of A is the sign of the numerator on those intervals because the denominator is always positive away from 0. For intuition, we can also visualize the number line. The expression a is positive to the left of 0 and between 0 and 2. It equals 0 exactly at x equals 2. And it is negative for x greater than 2. Remember, x equals 0 is excluded from the domain. Final answer. The sign of a is positive on the intervals from negative infinity to 0 and from 0 to 2. The function is 0 at x equals 2. It is negative on the interval from 2 to infinity, and it is undefined at x equals 0. In this lesson, we analyze the sign and domain of an absolute value rational expression. We'll carefully follow a structured algorithm: factor, apply absolute value rules, locate zeros, and build a sign chart. Here is our expression. A equals the absolute value of x minus 9 over the absolute value of x squared minus 2x. Step 1. Factor the denominator. X squared minus 2x equals x times x minus 2. Step 2. Use the property that the absolute value of a product equals the product of absolute values. So a equals the absolute value of x minus 9 divided by the product absolute x times absolute x minus 2. Step 3. Identify critical x values by setting each inner expression to 0. X minus 9 equals 0 gives x equals 9. Absolute x equals 0 gives x equals 0. And x minus 2 equals 0 gives x equals 2. Remember, the denominator cannot be 0, so x equals 0 and x equals 2 are excluded from the domain, while x equals 9 makes the numerator 0. Step 4. Build a sign chart across the intervals cut by 0, 2, and 9. Because absolute values are never negative, each factor is non-negative with a single 0 at its root. This lets us fill the sign table quickly, and then read off the sign of a. From the sign chart, we conclude the following. A is positive on all allowable intervals. A equals 0 at x equals 9 because the numerator is 0 there. And a is undefined at x equals 0 and x equals 2 because the denominator vanishes. Finally, state the domain explicitly and show the simplified expression one more time. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.